Welcome to this video on the performance applications of desiccant dehumidification systems. In this session, we'll assess how to evaluate desiccant systems and explore real-world configuration, effectiveness metrics, and emerging uses in HVAC design. In this video, we'll start by discussing how to quantify the effectiveness of desiccant dehumidifiers. Then we'll examine common system layouts that combine desiccant wheels with other HVAC components. Finally, we'll explore some advanced topics on real-world applications where desiccant systems are making a difference. By the end of this video, you'll be able to evaluate a desiccant dehumidifier's performance using appropriate effectiveness equations. You'll also be able to read a typical desiccant system layout and understand the function of each major component. Finally, you'll be able to evaluate whether desiccant dehumidification is suitable for a particular application, based on humidity control needs, energy consideration, and system integration requirements. So let's start with a question. Consider this carefully. Can you think of a space or application where it's crucial to control humidity, but not necessarily temperature? Maybe it's a supermarket where condensation on food packages must be avoided, or a museum where preserving sensitive artwork requires steady moisture levels, or a hospital operating room where patient safety demands precise humidity, regardless of room temperature. These are examples where desiccant dehumidification can provide target control. As we go through the video, reflect on how different components of the system contribute to this kind of precision. To assess the performance of desiccant dehumidifiers, we consider two types of effectiveness, one for mass transfer and one for heat transfer. Both are necessary because the system exchanges both water vapor and energy. The mass transfer effectiveness, shown in this equation, measures how close the actual humidity ratio of the process outlet air is to the ideal. A value close to 1 means highly effective dehumidification. Commercial units typically reach around 0.9. For energy transfer, enthalpy effectiveness is U. This is shown in this equation. It measures how far the actual enthalpy of the air leaving the process stream deviates from its ideal value, considering the energy content of the regeneration stream. Here, lower values are better. A typical system achieves values around 0.1 to 0.2. Most real-world systems integrate desiccant dehumidifiers with sensible cooling coils. The figure shows an example of such a configuration. Outdoor air enters at point 1, is dehumidified through the rotating wheel, and exits as dried hot air at point 2. The air then mixes with return air from the building, passes through a sensible cooling coil, and it is delivered to the space. Meanwhile, the regeneration stream passes through a heat reclaim coil and is eventually exhausted. This design helps maintain comfort while minimizing the need for reheat. Applications like supermarkets are particularly well suited for this kind of system. Since latent loads dominate, the desiccant system handles moisture, while the coil ensures temperature control. Regeneration is typically powered by natural gas, but solar-assisted systems have also been explored. While these desiccant systems can outperform conventional air conditioners under the right conditions, they are also more complex and costly upfront. However, since they can use natural gas and operate during times of high electricity prices, they can offer long-term savings. Liquid desiccant systems function similarly but introduce specific concerns. The salt solutions can be corrosive, and tiny droplets may escape into the Earth's stream. For this reason, filters or demisters are necessary, and careful material selection is important. Despite these complexities, both solid and liquid systems continue to see interest, particularly in applications like hospitals and industrial buildings, where humidity control is critical, or in the DOAS, where fresh air must be dehumidified independently from the recirculated air. So let's recap with some key takeaways from this video. The key to evaluating the Desiccant system lies in understanding their effectiveness at removing moisture and managing energy. They are most valuable in high latent load settings like supermarkets, hospitals, or outdoor air systems. Finally, the integration with HVAC components and the choice of regeneration energy source significantly affects overall performance and sustainability. If you are interested in applying Desiccant technologies in your designs, explore the OAS strategies where fresh air is handled separately from recirculated air. You can also investigate how solar or waste heat might be used to regenerate Desiccants in a more sustainable way. And from a broader perspective, compare Desiccant systems with conventional ones, not only in energy use, but in long-term cost and environmental impact. Thank you for watching this video.